Today, I'm going to tell you about seasonal evolution of ice ridges, about their consolidation and melt. Ice ridges are accumulations of ice blocks formed during dynamic events. Why do we care about ridges? Well, first, they cover from 10 to 40% of ice area depending on the season. Second, they play a key role in atmospheric and oceanic drag forces. Finally, their mass balance is very different from level ice. The ice growth of ridges happens inside of them, while ridge bottoms can melt not only in summer, as for level ice, but also in winter. After ridges are formed, the voids inside them are freezing, forming a consolidated layer. Thickness of this layer is typically compared with thickness of surrounding level ice. The fraction of these two thicknesses, also called a degree of consolidation, mainly depends on ridge porosity. So, what is a typical ridge porosity? Most ridges have around 30% of water-filled voids inside them. This gives a solution with consolidated layer being 1.8 times thicker than level ice around it. This theoretical 1.8 ratio of consolidated layer thickness and level ice thickness should define an upper limit of consolidation, because of two following reasons. First, ridges freeze on average less time than level ice around them. And second, ridges are covered with 2-3 times thicker snow cover than level ice. But observations on this figure tell a different story. They show that consolidated layer can be 2-4 times thicker than level ice around them, especially in spring and summer. To investigate this process, we used ridge observations during MOSAiC. Our ridge was sampled after its formation in January and later in July. It was studied using ice coring and temperature buoys. Coring observations, which you can see now, showed a strong spatial variability, with a strong consolidation in the central part of the ridge and weak consolidation at its flanks. Season evolution from buoy measurements showed that speed of consolidation was pretty slow but suddenly increased in mid-April. Isotope composition showed that ridge parts at the middle depths of the ridge, which consolidated after winter and experienced a rapid consolidation in spring, also had a large snow mass fraction, comparable to ridge porosity. This ridge rapid consolidation started right after the warming event in April. This warming allowed leads to stay open for several days. This led to a strong snow transfer into leads, with lead ice having 70% of snow mass after their refreezing. Right after the warming event, the middle part of the ridge experienced a rapid cooling. The depth of this cooling coincides with the depth of rapid consolidation and also of snow mass in ridges. Rare previous observations of ridge evolution showed a gradual consolidation. During MOSAiC, consolidation was initially very slow as level ice grows, but after warming event, consolidated layer became 3 times thicker than level ice. Summarizing the first part of this presentation, we suggest 3 different mechanisms of ridge consolidation. The first, the classical one, is via atmospheric cooling. This mechanism gave only 70 centimeters of new ice to the investigated ridge. The second, via snow-slush, which may reach a ridge keel due to divergent or convergent deformations. This mechanism gave more than 2 meters of new ice to our ridge. Finally, a small part of consolidation in summer may occur due to the transfer of meltwater into ridge keels. The second part of this presentation is about ridge melt. And here we wanted to answer a simple question. What is the difference between melt rates of level ice and ridges? The previous studies, they gave very different values. They range from 1.6 to 5 times larger melt for ridges. To answer this question, we use repeated ROV sonar measurements from MOSAiC. We've made several measurements of draft of ridge and level ice around it in June and July. The level ice areas included both thinner first-year ice and thicker second-year ice. In addition, we made several drilling transects and installed temperature buoys in both ridge and level ice. We observed that thicker ice was generally melting faster, with the largest melt for ridges, less melt for second-year ice, and the smallest melt for first-year ice. The ridge was melting 3 times faster than level first-year ice around it. Here you can see one of the ridge cross-sections with solid lines from coring and dotted lines from sonar, before in blue and after in red the melt observations. You can also see that the ridge was very consolidated, with only 4% of voids. We also see that the ridge melt was very heterogeneous, with point measurements from nearly 0 to over 3 meters for ice loss. To analyze the spatial variability of ridge cross-sectional melt, we simplified ridge cross-sections to trapezoidal shape, following the previous observations from Fram Strait. This allowed us to define main parameters governing ridge cross-sectional melt. This ridge contained over 100 cross-sections with melt from 20 centimeters to over 3 meters. The first key parameter was the ridge draft, with deeper ridges melting faster. The second parameter was keel slope, with steeper ridges melting faster. The third parameter we identified was ridge width, with wider ridges melting slower. We think that this is related to ridge consolidation, which is typically stronger for wider ridges. We also observed that ridge cross-sections located further away from the ridge front edge melted much less. Overall, we linked 60% of ridge melt variability to these simple parameters. Temperature measurements allowed us to distinguish surface and bottom melt for ridges and level ice. We found that ridge bottom melt was 4 times faster, with nearly identical surface melt for both level ice and ridges. Here are the take-home messages. First, we identified new snow-related mechanism of ridge consolidation. This mechanism may explain observations of stronger ridge consolidation in spring. Second, we used ROV sonar measurements to show that ridges melt 3 times faster than level ice, with even a 4 times difference for the bottom melt. We also linked most of ridge melt variability to their shapes, with deeper, steeper, and narrower ridges melting faster. Thank you for listening.